An argument is a conjunction of premises implying a conclusion. A conjunction of premises implying a conclusion. Formally, an argument is a compound statement of the form P1 and P2 and so on and Pn implies C. So here we have a conjunction implying C. P1, P2, all the way up to Pn are called the premises of the argument. C is called the conclusion of the argument. In philosophy and logic, arguments are often written in row-wise format. So you write your first premise, your second premise, all the way up to your last premise, and then you write, therefore, your conclusion. Here the triangular dots are a symbol for the word therefore. Let's look at a couple of arguments now. Number 1. If an integer is odd, then its square is odd. 5 is an odd integer. Therefore, 5 squared is an odd integer. 2. If an animal is a dog, then it barks. Fido is an animal that barks. Therefore, Fido is a dog. Let's analyze our first argument. If an integer is odd, then its square is odd. 5 is an odd integer. Therefore, 5 squared is an odd integer. We want to answer the following question. Is it a good argument? In other words, is it a valid argument? Let's look at the premises. If an integer is odd, then its square is odd. 5 is an odd integer. Our experience tells us that both premises happen to be true. Observe that if we have an odd integer 2k plus 1, where k itself is an integer, then its square, 2k plus 1 squared, equals 2k plus 1 times 2k plus 1, which results in 4k squared plus 4k plus 1. Now, in the first term, let's factor out a 2. So we end up with 2 times 2k squared plus 2k and then plus 1. This result happens to be of the form 2 times an integer. 2k squared plus 2k is an integer, plus 1. So our answer happens to be also odd. So it is a mathematical fact that if an integer is odd, then its square is also odd. This means that our first premise is true. Our second premise is also true, because 5 is actually 2 times 2 plus 1, which is odd. That means our second premise is also true. So what about the conclusion? 5 squared is an odd integer. Is it true or is it false? Since 5 is an odd integer, by the first premise, it's squared. 5 squared is odd. So we found that the conclusion is true. So here is our summary. We have this argument. Premise 1, premise 2, therefore conclusion. When both premises are true, that led to the conclusion being also true. So let's go back to our question. Is our given argument valid? Answer is yes. Why is that? Because all premises being true led to the conclusion being true as well. Now let's go and look at our second argument. If an animal is a dog, then it barks. Fido is an animal that barks. Therefore, Fido is a dog. In this argument, we again have premise 1, premise 2, therefore conclusion. Now let's assume that both premises happen to be true. So assume premise 1 is true, premise 2 is true. Let's ask the question, what is the truth value of the conclusion? Now, let's express our argument symbolically. Now, in our first premise, there are two assertions. An animal is a dog, an animal barks. So let P be an animal is a dog, Q be an animal barks, so our first premise is then P implies Q. If an animal is a dog, then it barks. Our second premise is an instance of Q, so we're going to call it Q. Our conclusion happens to be an instance of P, so we're going to call it P. Now again, we're assuming our two premises happen to be true. Now here, our second premise, Q is true. That automatically makes our first conditional P implies true. And we're saying that that happens to be true. Now, question we asked, what is the truth value of the conclusion? Well, if you look at P implies T, for it to be true, P could be anything. Recall that true implies true happens to be true, but also false implies true is also true. So in this particular argument form, we just discovered that even if we know the premises are both true, the conclusion could be anything. It could be true or it could be false. So now we're asking the following question. Is our argument valid? Is it a good argument? Well, let's answer that it is not, because we are not getting what happened in the first example. In the first example, knowing the premises were all true, that led to the conclusion also being true. That's not happening here. Here I am taking for granted that both premises are true, but I'm not getting anything about the conclusion. It could be true, it could be false. So we will say that this is an instance of an argument that's invalid. So our second example is an example of an invalid argument. Now, based on our two examples, let's now state what it means for an argument to be valid. That we call the golden rule for arguments. An argument form is valid if and only if, whenever the premises are all true, so is the conclusion. It is invalid otherwise. Here is a question. Suppose we have a valid argument form. Conjunction of the premises implies conclusion. What is the truth value of that conjunction of the premises implies conclusion? Let's look at that right now. So we are supposing that we have a disvalid argument. We want to find the truth value of the conjunction of the premises implies the conclusion. So let's think of this in terms of a truth table. So here we're asking, what are the truth values of the conjunction of the premises implies the conclusion? What are the truth values in the different cases of premises and conclusion? Now, let's take a look at all premises being true. So suppose all premises are true. In that case, because our argument form is valid, we end up with C also being true. So here we conclude that C is also true, because we're assuming all premises are true and we have a valid argument, then the conclusion is also true. Now, so what's in here now? We're taking the conjunction of true and in so on and true. Everything here is true. Implies true. Now, I'm trying to compute the truth value of that conjunction implies a conclusion. Now, when you take the conjunction of all true, the result is true. So whatever is inside the bracket, it ends up being all true. So now let's calculate what is true implies true. True implies true happens to be true. Okay, so in our first line, whenever all premises are true, the conditional conjunction of premises implies conclusion is true at the end. Now, there are other cases I would have to consider. another case I will have to consider here is maybe one of these is false, or maybe two of these are false. All remaining cases have at least one false. So let's say one of the premises were false. When we go here, in the conjunction, the result from that will be false, because the only case when a conjunction is going to be true is when all components are true. But in this case, one of the components is false, so then at that point the conjunction is false. Implies, now, whether I assume C to be true or false is now irrelevant, because we know that whenever the antecedent is false, the result of the conditional is always true. So if I know the conclusion is true, false implies true is true. If I know the conclusion is false, false implies false is still true. So in summary, it doesn't matter how many false entries I have here. My result is going, for the conjunction of the premises implies the conclusion is going to be true. So what's the answer to my original question? My original question is asking, we have a valid argument form, premise 1, premise 2, all the way to premise n, therefore conclusion. What is the truth value of the conjunction of those premises implies the conclusion? We have to say true. In other words, the statement form, conjunction of the premises implies the conclusion, happens to be a tautology. Because no matter what combination of truth values you put for the premises, the conclusion, your outcome is always true. So we conclude that it is a tautology. It's always true, so it is a tautology. So now, let's reverse the question. Does it follow that if the proposition conjunction of the premises implies the conclusion is a tautology, that it represents a valid argument form? Let's take a look at that now. So suppose the conjunction of the premises implies the conclusion is a tautology. Is the argument premise 1, premise 2, all the way up to premise n, therefore conclusion, valid? Now we need to remember that for it to be valid, for this argument form to be valid, we will have to have the following happen. Whenever the premises are all true, then so is the conclusion. So let's assume that all premises happen to be true. So assume premise 1 is true, premise 2 is true, and so on, all the way up to premise n is true. Now we're going back to our conditional. Conjunction of the premises implies conclusion. So we're plugging in P1 all the way to Pn is true. So we got true and true and true. All of them are true. Implies the conclusion. Now, since we're saying that that's a tautology, that means the result is true. Now, let's calculate. We know that the conjunction of all true is true. So that's True implies conclusion is logically equivalent to true. Now, what do I get for the conclusion here? Could it be false? Well, if it were false, true implies false. True implies false is false. It doesn't satisfy our hypothesis that it has to be true. So we have to conclude, yes, the conclusion can only be true. So in summary, we assumed that the conjunction of the premises implies the conclusion is a tautology. We asked the question, is our argument form valid? The answer is yes, because whenever all premises are all true, you must conclude that the conclusion is also true. It cannot be false. Based on our findings, we can rephrase the golden rule for arguments in an alternative form. In argument form, conjunction of the premises implies conclusion is valid if and only if it is a tautology. Otherwise, the argument is invalid. So here's what we're saying. This is a theorem. This argument form will be valid if and only if I know that the conjunction of the premises implies the conclusion is a tautology. This rule, the golden rule for arguments practical version, is what we're going to use to determine whether a given argument form is valid. So question, how to determine if a given argument is valid? Answer, determine whether its symbolic form, conjunction of the premises implies the conclusion, is a tautology. If it is a tautology, the argument is valid. If it is not a tautology, the argument is invalid. Let's exemplify. Determine whether the given argument is valid. Number 1. If an animal studies, then it is a dog. Fido is an animal that studies. Therefore, Fido is a dog. First step, convert your argument into symbolic form. Let P be an animal studies. Let Q be an animal is a dog. So here is our symbolic form. Premise 1 has the form P implies Q. Premise 2 has the form P. Fido is an animal that studies is a case of P. Therefore, conclusion happens to be Fido is a dog, which is a case of Q. Next, we form the conjunction of the premises implies the conclusion. premise 1 and premise 2 implies the conclusion. What we want is to construct a truth table for this compound statement. If we obtain a tautology, our argument is valid. If we do not obtain a tautology, then our argument is invalid. So let's proceed to come up with the truth table for the conjunction of the premises implies the conclusion. Now, conjunction of the premises. First premise, P implies Q. And second premise is P. Implies our conclusion, which is Q. Okay, so to construct a truth table, we need to come up with all cases of our components. There are two components, PQ. So we're going to come up with all cases for P and Q. So P, Q. True, 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 false, false, true, false, false. Now, in coming up with the truth values of our conjunction of premises implies conclusion, we need to break this up. We need Q. In order to compute this conditional, we need the truth value of Q, and then we need the truth value of P implies Q and P. So let's make two separate columns for that. Q, P implies Q, and P. Okay, Q we already know. True, false, true, false. We need to find out what P implies Q and P is. So for that, we need the truth values of P implies Q and also P. Now P we already have true, true, false, false. So we write them in. P implies Q, we need to recall our definition. True implies true is true. True implies false, that's false. False implies true is true. False implies false is true. Okay, so we need their conjunction. So we need and. True and true is true. False and true is false. True and false is false. True and false is false. Okay, so now that I have my antecedent and my consequent, I am ready for my conditional. True implies true happens to be true. False implies false happens to be true. False implies true happens to be true. False implies false happens to be true. So we conclude that our compound statement, conjunction of the premises implies conclusion, is a tautology. So what does that mean? That means that my original argument must be valid. Example number 2. The integer 7 is prime or it is even. 7 is not prime. Therefore, 7 is even. Again, we convert to symbolic form, form the conjunction of the premises, and build a truth table for it. So let P be 7 is prime. Q be 7 is even. Our symbolic form. Our first premise says 7 is prime or it is even. So it's P or Q. Our second premise says that 7 is not prime. So that's the negation of P. Therefore, conclusion, which says that 7 is even, which is Q. Okay, so this is our symbolic form for our given argument. So now let's form the conjunction of the premises implies conclusion. So premise 1 is P or Q. And premise 2 is negation P. That implies conclusion, which is Q. Okay, so now we need to find out the truth values of that conjunction of premises implies conclusion. Okay, so here are our cases. So we need P, we need Q. True, 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 false, false, true, false, false. In order for us to find out the truth value of the conjunction of premises implies conclusion, we need to know the truth value of the antecedent and the consequent of that conditional. So we need to know the truth value of Q, we need to know the truth value of P or Q, and negation P. P or Q and negation P. Now Q, we can just copy it. True, false, true, false. We need to figure out P or Q and negation P. There are two things we need in there. We need the result for P or Q. We also need the result for negation P. Negation P is immediate. False, false, true, true. For P or Q, we just have to remember our definition. True or true is true. True or false is true. False or true is true. False or false is false. Now we are ready for their conjunction. So and. True and false is false. True and false is false. True and true is true. False and true is false. Now that we have our antecedent and our consequent, we apply our conditional. Okay. False implies true is true. False implies false is true. True implies true is true. False implies false is true. So we conclude that our conjunction of premises implies conclusion is a tautology. That means that our given argument is valid. Example number 3. If it is Friday, I put my books away until Monday. I put my books away until Monday. Therefore, it is Friday. So, let's convert our argument into symbolic form. Let P be, it is Friday. Q be, I put my books away until Monday. Now, our symbolic form is, there are two premises. So, premise 1, premise 2. Premise 1 says, if it is Friday, then I put my books away until Monday. So, it is a conditional. P implies Q. Second premise says, I put my books away until Monday, which is Q. Therefore, it is Friday, P. So now I'm going to form the conjunction of the premises implies the conclusion. So premise 1 and premise 2 implies conclusion. My premise 1 happens to be P implies Q. P implies Q. And the premise 2, which happens to be Q, implies the conclusion, C, which happens to be P. Now we construct a truth table for conjunction of premises implies conclusion. Two cases, PQ, I'm going to put P and Q. So true, 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 false, false, true, false, false. What we need, here we have a conditional, so we need the antecedent and we need the consequent. The consequent P, we already have it. True, true, false, false. The antecedent, which is P implies Q, and the Q is a conjunction. So I need each of the components of that conjunction. We need Q, and we also need P implies Q. Q, we have it. True, false, true, false. P implies Q, we appeal to the definition. True implies true is true. True implies false is false. False implies true is true. False implies false is true. Okay, we need that conjunction. We need the conjunction between those two columns. True and true is true. False and false is false. True and true is true. True and false is false. Now we have what we wanted. We wanted the antecedent and the consequent. So now we can take the conditional, the implication. True implies true is true. False implies true is true. True implies false. True implies false is false. False implies false is true. Okay, so here's what we just found out. We found out that the conjunction of the premises implies conclusion fails to be a tautology. This one's not a tautology. What does that mean? It means that the given argument is invalid. Very good. Here is a summary from our 3 examples. In example 1, we found that the argument form P implies Q, P therefore Q is valid. The argument form in example 2, P or Q, negation P therefore Q is also valid. In example 3, we found that the argument form P implies Q, Q therefore P happens to be invalid. As it turns out, there are a variety of argument forms that are valid and some that are invalid. We shall introduce those shortly. Now let's study some terminology. Invalid argument forms, such as in example 3, are said to be fallacies. The word fallacies is plural of fallacy. More precisely, an argument which has an invalid argument form is called a formal fallacy. In our example 3, our argument form, our symbolic argument form is P implies Q, Q therefore P. It happens to be invalid because the conjunction of the premises implies the conclusion is not a tautology. So our argument is a formal fallacy. An argument which has a valid argument form but whose premises fail to all be true is said to be an informal fallacy. Our examples 1 and 2 have this defect. They both have valid argument forms, but when we scrutinize the premises, we realize that some are false. So in number 1, recall, if an animal studies, then it is a dog. Fido is an animal that studies. Therefore, Fido is a dog. If we look at the second premise, Fido is an animal that studies, does not appear to be a true premise. Unless Fido is a human being, this second premise is expected to be false. although we have a valid argument form here. So our first argument happens to be an informal fallacy. In our second argument, the integer 7 is prime or it is even. 7 is not prime, therefore 7 is even. This argument in symbolic form happens to be a valid argument form. But when we look at the premises of the argument itself, we realize that one of them is clearly false. 7 is not prime is a false mathematical statement. So, in this case, our argument has a valid argument form, but not all of its premises are true. That makes our argument an informal fallacy. We now conclude this discussion on argument validity. Certain valid argument forms are common and receive special names. Modus ponens is the argument form. P implies Q, P therefore Q. This happened in our first example. Here is another one. Modus tollens. P implies Q, negation Q, therefore negation P. Addition. P, therefore P or Q. The disjunctive syllogism. P or Q, negation P, therefore Q. Our second example had this argument form. The hypothetical syllogism. P implies Q, Q implies R, therefore P implies R. Adjunction. P, Q, therefore P and Q. On a separate installment, we shall focus on the art and science of establishing argument validity deductively. For now, we're going to exemplify establishing the hypothetical syllogism deductively by definition, also by contradiction. Let's begin. Hypothetical syllogism. P implies Q, Q implies R, therefore P implies R is a valid argument form. In order to establish deductively by definition that this argument form is valid, we need to use our definition of what a valid argument form is. That happens to be the golden rule. It says that whenever all premises are true, so is the conclusion. So let's assume that all premises are true, and let's find out what the truth value of the conclusion is. So assume P implies Q is true, Q implies R is true. Here is our goal. Establish P implies R is also true. That's our goal. Now, there are two possible cases for P here. P could be true or P could be false. So let's take the case when P is true. So case that P is true. What happens? When P is true, our first premise becomes true implies Q is true. But then this implies that Q itself must also be true. That's by our definition of the conditional. If we want true implies something to be true, that something can only be true. Now, our second premise, Q implies R is true. But now we know Q is true. So let's substitute. True implies R is true. Again, in order for the conditional true implies something to be true, that means the something has to be true by definition of the conditional. So here R is also true. Okay, that's what we get when P is true. Now we have to ask the question, what is the truth value of the conclusion? What is the truth value of P implies R? Now, we know P is true because we are assuming that. So we have true implies R, but we also know that R is true. Now let's calculate. True implies true is true. Okay, so we just arrived at the conclusion being true when P happens to be true. Now, our other case is, what about if P is false? Case P is false. Now, that one is very simple. If I go and substitute P being false in the conclusion, then we get that P implies R becomes false implies R. But we know by definition of the conditional that will end up being true, because false implies false is true, false implies true is true. So regardless of R, the conclusion turns out to be true. So our goal has been achieved. We established that P implies R is true under the assumption that both premises were true. Now, let's establish the hypothetical syllogism by contradiction. Here we have the hypothetical syllogism. To establish the hypothetical syllogism by contradiction, we are going to assume that all premises are true, but the conclusion is not. Then we proceed to find consequences of these assumptions and try to obtain some contradiction. Once we've reached the contradiction, we are done. So let's begin. We're assuming all premises are true. So let's do this in steps. Our first step, P implies Q is true. That is one of our hypotheses. Step 2. Q implies R is true. That's also one of our hypotheses. Three. P implies R is false. That is our assumption. We're going to call that our RAA hypothesis. RAA stands for reductio ad absurdum. Now, if we want P implies R to be false, there is only one way that can happen. P being true, R being false. So we get this by definition of the conditional. In step 3. Now, let's observe that in step 1, now that P is true, we can substitute. So we obtain true implies Q is true. This can only happen when Q is true itself. Okay, so in step 5 we have a substitution, and we are using steps 1 and 4 in that substitution. Step 6, Q is true. That follows by definition of the conditional. In step 5. Now, let's make use of R now. So, in step 2, Q implies R is true. When we substitute R by false, we obtain Q implies false is logically equivalent to true. So, here we are substituting, and here we're using steps 4 and 2. Let's observe that Q implies false is true only when Q is false. That's by definition of the conditional in step 7. Okay, so let's step back and observe that we have obtained a contradiction. On the one hand, in step 6, we concluded that Q must be true. But then in step 8, we concluded that Q is false. That's a contradiction. So Q is true and Q is false. That comes from steps 6 and 8. And this is a contradiction. Now that we have reached the contradiction, what does that mean? That means that our assumption that all premises are true but the conclusion is not cannot hold. So, what does that mean? That means that we must have that all premises being true leads to the conclusion also being true. So the conclusion must be true. And that completes our proof.